Question 6. An astronomer uses a spectrometer and diffraction grating to view hydrogen emission spectrum from a star. The light is incident normally, so that means at right angles too, normally on the grating. So what have we got? The first order spectrum from 3 different colours. Part A. The first order diffraction maxima are observed at angles 12.5, 14 and 19 to the direction of the incident light as shown in figure 6.1. 2 of the wavelengths are 4.33 10 to the minus 7 and 4.84 10 to the minus 7. Calculate the wavelength of the third. So if I needed to calculate the wavelength of the third, I'll need n lambda equals d sine theta, the diffraction grating equation, and lambda would be d sine theta divided by n. N would be the number 1 because it's the first order. What I don't have is a value for d, so I need to calculate d using one of the wavelengths and angles that I already have. So up here, n lambda equals d sine theta. I'll have to rearrange to make d the subject, and that's going to be n lambda divided by sine theta. I'll need to pick one of these angles and wavelengths, so I'll just choose the first one and put the numbers in to calculate my d. So n is going to be the number 1 because it's the first order, times the wavelength, 4.33 times 10 to the minus 7, divided by sine of the angle 12.5. And on my calculator, that's going to produce 2.00 times 10 to the minus 6 meters. I can then use that in this equation over here. So the distance between slits on my diffraction grating is 2.00 times 10 to the minus 6 times by sine of the angle that I haven't yet got a wavelength for, so that's going to be 19.0, divided by the order number, which is the first order, so number 1, and that will produce a number for me of 6.51318 times 10 to the minus 7 meters. But because all of the numbers in the question are to 3 sig figs, I need to write my answer to 3 sig figs, so that would be 6.51 times 10 to the minus 7 meters. Part B, in order to increase the accuracy of the values for wavelength, the student decides to look for higher order diffraction maxima. Part 1, state how this increases the accuracy. Well, each of these angles is going to have associated with it a certain absolute uncertainty of plus or minus, should we say, 0.1 degrees. This is going to be 12.5 plus or minus 0.1 degrees. And that plus or minus 0.1 degrees will be the same for all angles. So when you're looking at the percentage uncertainty, the bigger the angle, the less the percentage uncertainty for the same absolute uncertainty. So if you need to revise your errors, take the opportunity right now to revise those errors. So let me communicate that as best I can on just 2 lines. I'm going to need more space than that, so I'm going to start up here. A larger order will be found at a larger angle. A larger angle will have a smaller percentage uncertainty. All angles have the same absolute uncertainty, plus or minus 0.1 degrees, for example. Part 2, calculate how many orders n can be observed for the shorter wavelength given in Part A. So the shorter wavelength given in Part A is 4.33 10 to the minus 7, 4.33 times 10 to the minus 7 meters. So using the diffraction grating equation, n lambda equals d sine theta, what this is asking for is what is the absolute largest angle that you can have in this equation. That's going to be 90 degrees. Sine of 90 is 1. Rearrange to get n as the subject. That's going to be d sine of 90, which is 1, so I'm just going to leave that out, divided by the wavelength. So d is 2.00 times 10 to the minus 6, which comes from up here, divided by the wavelength, 4.33 times 10 to the minus 7. Plugging that into my calculator, I get 4.619. Now this is important. So the max order number is, I can't round up, I can't have half an order, I have to round down. Even if it was 4.999 recurring, the maximum order spot that I could achieve here is 4. 4. No sig figs there at all, just the number 4. Part C, the 3 emission lines all arise from transitions to the same final energy level. The part of the energy level diagram of hydrogen relevant to these transitions is shown in figure 6.2. Draw lines between the energy levels to indicate the transmissions of which cause the 3 emission lines and label them with their wavelengths. Well, if they all have to end at the same final energy level, then that means that would be 1, 2, and 3. This one would be the biggest energy change, the highest frequency, the shortest wavelength, so that's 4.33 times 10 to the minus 7 meters. This one is the smallest amount of energy, the lowest frequency, and therefore the longest wavelength, the one that we calculated, 6.51 times 10 to the minus 7 meters. And this one would be the one in the middle, 4.84 times 10 to the minus 7 meters. Hopefully that's all of that single mark nailed there. Part 2, there are other possible transitions between the energy levels shown in figure 6.2. The least energetic of these produces photons, so this is an energy, of 4.8 times 10 to the minus 20 joules, and that must be associated with this energy transition here at the top. Calculate the wavelength of these photons. State in which region of the electromagnetic spectrum this wavelength is found. Well, this is relatively straightforward. Let's use Planck's equation, E equals hf. Substitute in the wave equation to end up with hc over lambda. Rearrange to make lambda the subject. hc over E. Plug in the numbers. 6.63 times 10 to the minus 34. Planck's constant times the speed of light. 3.0 times 10 to the 8 divided by the energy given in the question, 4.8 times 10 to the minus 20 joules. Plug that into a calculator and I end up with 4.144 times 10 to the minus 6 meters. Good manners, I'm given this to 2 sig figs, so I need to limit that to 2 significant figures. 4.1 times 10 to the minus 6 meters. And whether you know it or not, the particular wavelength boundaries between different parts of the electromagnetic spectrum, below the visible range, below red, but above microwaves, so this would definitely be infrared. Done.